The various engineered wire rope manuals discussed above have tables for total steel area, cable weight, cable strength properties, and cable stretch. Specifically, cable strength and stretch properties need to be adjusted based on their use conditions, and I'll discuss that below. These values that you should be using during your design for cable properties are in the EIA Bridge Binder, Volume 2 for design. So the cable stretch can be divided into structural stretch and elastic stretch, as described by the Tiger brand manual. You may also hear us call structural stretch as construction stretch. And this varies with the type of wire rope construction and occurs as the strands adjust under loading and settle into interstitial spaces between the strands. So, the cables aren't exactly a solid unit. They're different strands, and these strands are going to move around, rub against each other. They're going to settle, and as we stretch the cable, that area is going to reduce. It can vary between 0.25% to 1% of the span, depending on a light or heavy loading. And we don't know exactly how this is going to settle, so that's why we high hoist the cables and wait 24 hours to let this settling occur in our construction process. It's also important to note that this is not an elastic process, so it's not reversible, and it really depends on the history of the cable's use. Because we don't always know that perfectly, once again, we have the standardized process of high hoisting and waiting for the construction stretch or the structural stretch to come out. Now, elastic stretch is proportional to the load and length, which can be calculated by Hooke's law, PL over EA, which you may remember from the custom sag analysis lecture. This obviously varies greatly based on the chosen elastic modulus, and for our type of wire rope construction, the suggested elastic modulus is between 13.5 and 15 million psi, or the 93,000 to 103,000 newtons per millimeter squared range, which varies for up to 21% loading, so most dead loads fall under that range, and then between 21 and 65% loading, which most live loads fall under this range. So this for a new rope, I'll mention, will stretch significantly more as the cable wires settle. So for new rope, we'll want to use the empirical value of 110 newtons per millimeter square. Now, another important thing to discuss is sheave properties. And the cable end condition for our construction method is considered a sheave, where the wire rope loops around the cable. We'll take the sheave tread diameter as the inside diameter of the loop formed by the cable and the anchor, which we can measure in AutoCAD. Sheave properties are important because the amount of bending of the rope will stifle the movement and adjustments of wire strands and cause more wear over time if done incorrectly or too tight. And I tried to draw a little example here for you in this section AA to show where that increase in friction between the strands would occur. Rope strength efficiency depends significantly on that sheave tread diameter. And another important factor is groove size. Too small of a groove will have the same effect. It will pinch and create wear, while too large of a groove doesn't provide adequate support. So ultimately, due to the site conditions, some reductions must be made to that nominal cable strength reported in the manuals. And the conditions are as follows. We'll take a 15% reduction for the cable being used, 10% reduction for the cable being galvanized, and then due to the sheave condition and the turn back diameter, we take a 10% reduction because that sheave size is below the minimum ratio, which is reported in the Crosby tables. There are a variety of reductions. Applying them continuously would result in an extremely conservative number for cable strength because it is highly unlikely that cables will see a full live loading, and a factor of safety of 3 is already applied. We'll take the ultimate tensile strength reduction of 85% to account for all of the conditions above. And just as a reminder, not 85% reduction, but we're going to take 85% of the nominal value to be our ultimate tensile strength value.